Up next, I'd like to introduce our speaker, Michael Winterrose. Michael is a data scientist at Northrop Grumman Aeronautics Systems in the Advanced Manufacturing Technology Group. He's a focus on data pipeline development and machine learning for forecasting, anomaly detection, and computer vision. With over a decade of experience in defense analytics, artificial intelligence, and simulation, he has developed data-driven solutions to complex problems across an array of domains. Please join me in welcoming Michael.
Thank you. Okay, thank you very much. It's a pleasure to be here. I spent a number of years up the road here at MIT Lincoln Laboratory, so it's great to be back, the MIT family, and back on Cambridge, beautiful Cambridge. I really appreciate the invitation. Okay, as I said, coming from you from Northrop Grumman. Let's see. Today I'll be speaking about some systems that we're developing. We specifically work on aerospace manufacturing at scale. So we have large manufacturing facilities in north of Los Angeles. And let's see, jump into here, come to you as part of the Advanced Manufacturing Technology team. Our goal is to drive digital transformation at Northrop Grumman. So we work across a number of different areas. My specific area is AI, ML, and data. As a data scientist, we also work across connected workers, all kinds of IoT architectures, augmented reality, different ways to secure communications, and also cybersecurity. So a number of different missions, a medium-sized team that has a very large mission, so certainly thinly spread, and that'll be some of the techniques I talk about today, help us to multiply our force factor to achieve some of these missions. So, where I come from in the high desert of Southern California, it's a very sunny place, a lot of sun, but typically on a typical day, I face these two dark clouds, often over and over again, where I face both small training data set size and also imbalanced training data classes. So these are also other factors, but these are factors that we hit right away as we try to train our models. So both that our data often has not been, although it's generated potentially in great magnitudes, it's not typically been collected or stored in large amounts. And also when we do have data, often, a good thing for manufacturing, the target classes that we want to detect or prevent are anomalous or very small. So we have to deal with those two factors because our processes are very optimized and very streamlined and efficient. So, there's not often problems, but when there are problems, they can be very impactful to the system. So the first, I'll talk about a couple of use cases here. The first use case is enhancing industrial augmented reality on the production floor with machine learning. So, a big drive is to digitize a lot of our processes. Augmented reality is a big technology for our group. And basically, this fulfills a number of different things. It can be remote assist, displaying work instructions, things along this nature. Essentially, these are very rich sensor suites that are collected, that are being worn by the workers on the production floor, potentially collecting a large multimodal set of data. And so how can we leverage this? The machine learning isn't typically built into these devices. This large quantity of data that is challenging in many ways that we'll get into because it's egocentric, it's collected from sensors on the workers' heads. So it moves around, has very sharp angles, has a lot of noise, blur, things like this that we have to deal with. So just to give a sense of some of our technology stack, we typically do try to build at scale. We have a lot of systems we have to connect in. So we make big use of tools like AWS, machine learning and SageMaker, S3 for data storage, Lambda for coordination and connecting different tools. But I should also mention that we work across a lot of different types of environments, and we can't always guarantee, we would optimally love to have the cloud everywhere. We don't have it in all environments we need to work in because of the nature of the products that we work on. So we also always make sure that we produce and generate our tools such that they can operate both offline and online with a cloud connection. And just, to give a general sense, this is a stand-in problem. This is not typically exactly going to be this type of problem, but the type of problems we face are either a detection of foreign object debris, or also a validation or a detection if the configuration of certain kitting trays or different types of tooling are off. This is a at-scale production facility. This is just a surrogate problem where we have a toolbox that could be missing tools. These are typically prepared off-site and then brought onto site for the production floor. The worker is going to see a lot of these, and if we can detect automatically that something could be off with the tray, could save a lot of time on the production floor when these tools are getting ready to use, or also if there's configurations of the actual product that need to be corrected. So, typically there's a large suite of sensors. We would begin with just pulling the video off of that, pulling the JPEGs out of there, then converting that to a numeric format, and then processing machine learning on it. So typical, nothing surprising there, but some of the more challenging things come as we try to deploy this. A typical tray would be everything there. There's a number of anomalous, very long tail type problem where there could be a lot of different things could be wrong to try to work that out. So, it could be extra pieces, things missing, extra tools in the wrong place. And these are all things that are encountered and cost a lot of time on the production floor. So some challenges of this type of data, specifically where the sensors are on the workers' heads. We have sensor blur, certainly from the sensor motion. We have user-specific artifacts. Different people are going to move their heads different ways, of different perspectives, different heights. All this generates noise in the data set, and also artifacts from the holograms are projected into the actual data streams themselves. So, kind of the first use for machine learning in this pipeline would be to clean the data. So there could be two possible strategies to deal with this type of noise. We could train a large neural network that's robust to these things, or we could try to filter it out. We find it most efficient to filter out. So we deploy several layers of machine learning to filter out the initial data set where we're rejecting noise, blur, artifacts, and trying to keep our data as clean as possible to train that in. And then on top of that, as I said, a lot of the things we want to deploy are specialized or anomalous. So we also bring in to enhance our training data set, generative AI, diffusion models. There's different layers of this and different things that are useful, kind of at the simple layer. It's pretty easy to deploy some of these diffusion models to generate, precise pictures of foreign object debris. So in aerospace manufacturing, what we call FOD, or foreign object debris, is a very big topic. If you've ever been in one of these large facilities, you will see, quite a number of signage in almost every viewpoint that's extolling the workers to watch out for foreign object debris. So it's a big topic. We can generate automatic detection of that. And so some of these common objects are easily generated by the current diffusion models. And then we have specialized methods where we can also generate on some of these long-tailed items that are out in the tail of the distribution to be able to detect those. So, on this application, 2 layers of machine learning, both the generative AI and then for the detection itself, convolutional neural networks or transformers, can detect that typically in a efficient way once we've actually cleaned the data. So just give a sense for what this may look like. On the left, we have our data quality detection. Our data sets are typically very noisy coming out of these headsets. If we have a baseline in the blue there, not getting learning across that with a noisy data set, as we clean it, we have a very large jump up in performance of that model. As we are able to diversify our training set, typically we have a very small training set. In the lower right that chart, we have overfitting going on with the blue baseline curve where we've used traditional augmentation, flips, rotations, zooms to diversify our data set. If we're, in addition to that, injecting diversity of view, diversity perhaps of items, because our training data set typically can't cover all items we may find on the production floor, things like this. If we have a test set, we get a much higher learning performance out of there. And just some typical things that we may pull out of there. There's also domain adaptation techniques that we bring into depending on the use case. So a number of different use cases. And on the upper right there, we have some typical identification of FOD. That could be metallic FOD, that could be non-metallic FOD, and also the configuration. And also important, as we, of course, deploying the production floor, we're dealing with a lot of people that aren't versed in machine learning. It's really important for us to be able to give them, at least a heat map or interpretation of the model. Also, we store this in our databases. We go back in time and look at how our model's performing. Here's a GradCam type heat map, but this is certainly an important aspect of this to be able to deploy and have people trust what we're doing. Could be people who never experienced neural network or things like this. And where this is going, of course, the threshold and the generality of the large language models is unprecedented. The threshold has been lowered tremendously to use them, and the ability, the generalization of those intelligences are tremendously growing today. So, this is leading to our ability to actually generate courses of action and actual prescriptive analytics for this type of use case. So really all of our machine learning layers are now being rolled in and generalized by, an agent type framework with a large language model in the brain of that agent. So, agent-based frameworks, not a new topic. I worked a lot of these at MIT when I was here for a number of years. But really, of course, that's happening today with the generative AI and the breakthroughs in large language models, transformer models is tremendous. So we're certainly making use of these, driving towards agentic workflows and making this, once we have our predictive layer, we're able to then optimize this and go into the prescriptive and actual action course of action generation to be able to actually either tell a human what to do, or in some cases take actions and automatically for what can be done for these different use cases. So it's one use case. I want to get into this other, predictive alerting in manufacturing environments. Some of our products that we work on are very sensitive to temperature and humidity. And this leads to a very strict need to be able to maintain thresholds in temperature and humidity. We work in a challenging environment. In the summer times where our production facilities are, it can reach near 115 degrees. And the facility needs to be much below that. And during the day, roll-up doors can open and heat can flood in from the Mojave Desert, this type of thing. So it's very important for us to be able to predict this and control it in a proactive way. When conditions go out of threshold, it can have a very large impact, both financially and operationally. The material has to be replaced, can take a long time to replace it, can also have a large cost. Things have to be thrown out if it's out of spec for a certain amount of time. So a very important use case. To build this, we've constructed an IoT architecture where we have sensing nodes spread throughout our production facilities. These are enhanced with a feature matrix from outdoor conditions and also operating conditions within the environmental system. And this is then fed into different layers. We've done a number of things with this. We've generated digital twins. This enhances some of the data sets we based on our digital twins. We have rapid situational awareness layers, and then also feeding into machine learning that then can feed back on both of these layers to help us predict. So, never in different sensors. And basically the idea here is that for each sensing location, we can collect both the history of these key variables within those locations, and then also have the external environment for each of those going way back in time for our facility. And then we're able to match those up. And for each sensor, we can have a specific prediction for that location, what in the future, up to 10 days in the future, based on the government forecasting database that are available to us, can forecast what that's going to be out 10 days in advance. So instead of being reactive, which has been in the past, where we're just reacting to what's happening, sometimes actually until it crashes the threshold, and then it's being reacted to and can take several days to bring back down. These facilities are very large. We can actually hit that with a predictive ability to know 10 days in advance, 2 days in advance, get more and more accurate as we come up. It's that type of use case. So let's see here. And just to give another sense, basically, in this deployed environment, we try to keep things as simple as possible, because a lot of things can go wrong in deployment. It's more complex than you would think to actually deploy these things at scale. So as simple as possible and as robust as possible, because a lot of times people operating these systems are not going to be trained in how to actually deal with these algorithms. So here, just another representation. We have our feature matrix coming from the external weather. We have the target variable coming from our facility sensors, putting it into machine learning models. We often find that tree-based models can perform very well here, very efficiently. So things like XGBoost, gradient boosted trees, things like this. Often trying to draw a threshold or train a regression model prediction, and then compare that against what we've predicted based on what actually happens and iterating through that. So a traditional machine learning flow. And a lot of other models are possible on this type of data, but really to keep things as simple as possible in the algorithm aspect of this is important. And just to give another sense of the data, so we have the humidity, all kinds of different variables we can collect, looking at the different types of correlations. And also important in this is that we put an interpretation layer, of course, to be able to see what's driving our prediction, see if it makes sense, and see if it's consistent across different seasons and things like this. So. And if we're getting to some of the challenges, again, we revisit these dark clouds. Everyone else enjoying the sun, and I have these dark clouds we're fighting with. We have small label training data. Again, if we're looking at trying to predict like a daily max, and this temperature humidity data maybe hasn't been persisted over time, we basically get for each sensor, 1 data point per day. So it grows very slowly over a number of years. And also we draw a threshold. We're not typically going to be out of that threshold because it's very costly. We definitely invest a lot of resources to be able to keep that below. So the actual threshold events are also rare. The breaching of the temperature humidity is going to be a rare event, and also in a small data set. So let's see here. So to be able to also generalize this and make it more performant, we're also bringing in a synthetic data generation capability here. It's a little different. Here we're dealing with tabular data or time series. So we have a baseline that's certainly imbalanced, big challenge. We're not getting very good performance on being able to detect those defects. I should say, for us, it pays off a lot to be able to play with the synthetic data or the early training data to try to enhance that as opposed to the algorithm end, because a lot of times when these get deployed, people that may be dealing and trying to redeploy these algorithms aren't going to be able to have a lot of sophistication to be able to change them. So it helps us be able to bring that sophistication to the training data set and keep the actual machine learning pipeline as simple as possible. So trying a number of different techniques, a typical technique, also looking at GANs, how they perform, and then generative pre-trained transformers. If we look across this just to see performance, we actually find a lot of performance out of the transformer-based models, a very high ability to model the conditional distribution between the columns of data. We basically map this into like a language type problems, and then are able to get in this case, open source GPT-2 model to predict the next sequence out of there and be able to predict, generate these synthetic data sets. And there's some libraries that help with this. Also, we get a fairly good performance out of the generative adversary network, but certainly the most performance and most ability to model these complex distributions out of the transformer model. So just to give a sense for, kind of what synthetic data brings to our game. So we have a small data science team. As we say, most people would be manufacturing engineers, most people on the floor. So just very small. We need to multiply our ability to have an impact. We typically deploy our own sensors, right? We configure them. It takes a lot of work to collect real world data. Typically, we'd have a linear fixed workflow where we've seen projects in the past. We're deploying sensors, collecting data, doing the best we can, and then typically the project would end. But by iterating on these synthetic data flows, we're able to accelerate and become more dynamic in the team, able to multiply. Basically I can sit on my GPU cluster and generate thousands or millions of images or thousands or millions of tabular data points that can then train the model much more efficiently, multiplies my ability. Of course, real data is king if we can get it, and that's always going to be, most representative of the distributions. But we're able to generate a large variety, a large diversity of data. This really makes us more dynamic and more efficient, both across image data sets and also tabular data sets and time series. So, kind of a new thing is with the revolutions in NLP that we're making more and more use of those and trying to open up more of our data sets. But certainly across all these different modalities, we have a lot of impact. So with that, just to give a quick summary. Of course, as we've talked about, everyone's talking about a tremendous potential for AI and ML in manufacturing in general. And specifically, there's a lot of low-hanging fruit in some of these type of manufacturing that are difficult to get at and haven't been optimized at this point. Challenges, certainly small training data, imbalanced training data, and then also you could have concept drift and things like this. Covered a couple of case studies, predictive alerting, also detection of foreign object debris and configuration validation. Something I haven't touched on, this also touches additive manufacturing, where we can have similar image and multimodal data sets that can affect that and try to also work with that. We have an additive manufacturing team, and we work with them also to try to do predictive in situ monitoring. Let's see, in just a summary, so significant promise. Potential for manufacturing hampered by the dual difficulties of labeled training data set and also small target size of the labeled data set. Leverage to generative AI for synthetic data creation. It helps it be much more efficient, dynamic. And we've detailed specific developments of this fraud detection and also environmental alerting. And of course, there's a lot of low-hanging fruit. So this is just the beginning as we roll forward, and really important is for us to get simple use cases working, and then we get a lot more leverage on the production floor that people may be very skeptical, and we're able to leverage in that in a lot more application. So thank you for your time today, and acknowledge some of the development team, and feel free to reach out with any questions. Thank you very much. Either one.
Yeah, really exciting talk. I was curious, for the simulated image data, if there were any cases where you weren't able to generate images that sort of accurately reflect the real world, where sort of ray tracing was wrong, and what you did if it happened.
So it gets more complex as the image or the scene we're trying to replicate becomes more complicated. Kind of the simple use cases, a sharp metal screw or a bolt, we're able to generate those from pre-training. For some of the more sophisticated things, we'll train in things like image to image. There's different ways to take an image and then add noise and then take the diffusion process back down to bring it into the neighborhood, back into the image manifold. So those are the type of things. So I'd say the more complex use cases are still works in progress. And this would be things like a whole, like I showed the configuration tray, a complex tray could have a lot of different parts. That typically not going to be something we can generate just from a text to image model, but we would be doing, more sophisticated. These models are flexible, things like image to image, or also image to image plus a text prompt to generate that. And then also to bring on top of that, we can also train specialized neural networks to do domain adaptation across there. So that's also an aspect we bring in. So, we haven't been able to treat every single use case, but, we're trying to start as simple as possible, this philosophy of simple first. The things like fraud detection, small pebbles, things like this, certainly we can generate large, diverse data sets, and then working up to these more sophisticated use cases. Yeah. So, and we're certainly blessed to leverage the large explosion in development of these type of models today. Yes.
So my question's around, you're talking about different types of offline data, online data, right? Data can't cross boundaries for various reasons. Have you guys done anything around federated learning models? And then kind of what's your experience there, and have you been successful in deploying and not being able to reverse engineer those models when you're doing that?
So certainly something that we're looking at, federated learning across both, some of these applications for the data sets I've shown, and also, so certain additive manufacturing applications where it's not easy to transfer data set at scale, and that we're also bringing. So yes, we've looked at federated learning. I think this is a solution certainly for exactly what you say, across different types of manufacturing environments. With these synthetic data sets, an aspect of this I didn't bring in is that they can also anonymize data sets, and you can have some secure guarantees for anonymization. Something we've looked at, it still is challenging. Sometimes when you talk to security folks or something, they're not going to necessarily know what federated learning is. I see it as a solution that I've been pushing and that I could push into the future. To this point, I wouldn't say that we have deployed federated learning solutions, but I do see that as a solution for the future for a lot of these use cases also. In addition to synthetic data, those together be powerful partners. Thank you. Thank you for the questions.